Let's start our afternoon session. Our first speaker for today afternoon is Miguel Jiménez.
First and last. There is only one, I believe.
No.
No.
It's a coffee break.
And
then there are two more.
I know. Before coffee break, of course. I say.
And he will talk about. It's very big title, you know.
Yes.
Consequence of
Kalandiya.
Method for the solution of the wind theory equation.
Wind.
Wind
is what's written here. Wind, yeah. Wind.
Okay, let's go.
Good afternoon. Thank you for the invitation I received to be here. Let me say only 2 words about the conference today. I met Professor Natig in other activities 2 or 3 times, probably in the National Congresses of Mathematicians. I don't remember very well. But from my friend, I know he's a good mathematician, but also everybody talk about, as a person, his quality, human quality and so on. So for that reason, when I was invited to be here, I accepted immediately. It's a pleasure for me to present my modest contribution, and I wish you still more long life and new success. And also that we together with you for celebrate together. Okay, and the talk we present today is concerning progress in approximation theory, but also in general analysis. And I don't like to speak only for a speak. I like that everybody can understand a little, at least. And for this reason, I will not go so deep in many results, but the basic idea. And I hope at the end, everybody know at least what I'm talking about. Okay? And since this conference treats with mathematical physics, I decided to present something that, in my opinion, is very important for approximation theory, and was born together with a solution of a work of Kalandiya. I don't know exactly, probably it's a Russian mathematician, but perhaps it's coming from another part of the former Soviet Union. I don't know exactly. Before to go there, I will say a few words about the basic ideas in approximation theory. Excuse me, I know it's elemental thing for people that are working in this field, but for all who are far, it would be better to know. It's very easy in any case. We have a normal space E. We have a set in E, probably a linear subspace also. Usually, this is a space of continuous functions. These are polynomials, algebraic or trigonometric. And they are included in this way. They are increased in sequence of set in general. And the closure of all of them is dense in the set. This is the case, for instance, C01 and the polynomials. Well, now, thank you very much. Now, we are talking about the so-called best approximation. What is the best approximation? We take an F that belongs to a space E, and then we are searching for, looking for an element, Pn star, that depends, of course, F, such that for every element in Pn, we have that this polynomial or element is the one to reach the infimum, the distance, no? And this is for what it is called best approximation. There are many problems concerning existence of best approximation, uniqueness, how to calculate them, etc. Now, in general, it's very difficult to calculate exactly the best approximation, although there are different algorithms that work very well. But instead, we usually are searching for the good approximation. What is the meaning of a good? Is another element Pn tilde in the same space? that is in some sense approach to the best one. No, it's not exactly, but that is life. In general, we are looking for a lady who wrote more or less. It's the same thing here. And then now, after that, we fix another space F with the norm F. Usually in the E, usually this space has the norm, the space E plus another semi-norm. No? In total, this is a norm. For instance, we can have E space of continuous functions. We can consider differentiable functions, and then to write to use in the space of differential functions the norm of the subnorm and the subnorm of the derivatives. This is because it is since the derivative of a constant function is 0, then it is not a norm, but a semi-norm. Then we now try to solve the same problem in the following way. Direct result. What does it means? Well, to find a projection, an operator from this space F that we have here in the space of the approximating set in general, probably we use later polynomial Pn, such that they give approximately the best approximation. It means a good approximation. This is a direct result. There are many, for instance, Fourier series. You can take the partial sum of the Fourier series. There are many different ways to obtain direct result. And inverse results are just the contrary, in the sense that we have some estimates of the degree of convergence of this set to the function f, and we have the following question. Is the degree of approximation follow a certain rule? No? Then perhaps is it sufficient to say that this function belongs to the space if, no? Ff. These are called inverses. Well, the problem we are going to consider now is in the following case. We have here E is a space of continuous function on an interval, or perhaps periodic function is also more or less the same thing. And we consider as if as the space F the space of functions that satisfies Hölder conditions. I will recall the condition very fast, but in a few minutes only. But it's the general case. And then we are looking for this kind of problem in these spaces. This is a problem. I say that the first result known, or at least the only one, the first that I know, was a product of the Kalandiya method that I will show you now for solving the equation of the wind. It is written there, wind. It was a problem when we were working with the editor, I'm sorry. I only discovered it 2 or 3 days ago when I was taking a look to the sorry, I need to do it this way. Kalandiya is this one, no? Okay. Don't be afraid. Russian is not so difficult. And then anyway, we don't need Russian now. It's the title of the exposition. Ayúdame un poquito y córreme ahí para arriba otra vez. Sí. Gracias, Ratu. John Cuban, I believe that I can do that as a former the Russian in Moscow. Well, this is the title of the paper of Kalandiya. Kalandiya. It is he wrote his dissertation. Candidate dissertation is the name there, and it is published in the ¿cómo se llama? Matemáticas Sbornik, and in 1957. And now this was aquí vamos a poner esto. Okay, yes. This was the equation that he intended to solve. He intended not, he solved. he gave a direct method for the solution of this integral differential equation. Here, gamma is the unknown functions. F and B are given functions. But the main problem, consider it, is that all these functions, F, gamma, and beta, satisfies the Hölder conditions. This is why Kalandiya needed to set different results about approximation in the Lipschitz spaces. And that time there know nothing about that. He was the first who, ponme la que termina en 57.
By the way, he calls that theory of wind.
Wing, W, wing.
Not of the wind.
No, wing, this kind. Wing.
Right, okay.
Sorry, I expressed in the dito.
No, I am sorry that I know Russian, so therefore I can feel this difference. Okay.
I know.
No, this is,
I continue now, but I know you know. I continue, you know Russian. That is the reason for which I didn't intend to speak in Russian. Right? No, but it's clear that this was a paper also with the application to the elasticity theory.
by the way, his name doesn't seems to be Russian name, meaning that, well, it's everybody who speaks Russian, they call them the Russians, but this guy seemed to be not Russian. Probably Georgian or something like that.
Soviet.
I thought
it's not a Russian name. No.
I know, but I told at the beginning just that I don't know.
No,
if
you said Russian scientist, so she's not Russian.
Soviet.
No.
Science.
Okay. But it's okay. I'm sorry.
No, you are free to, please, you are main invited here.
Exactly.
No problem. But I said, probably I didn't say it, but I thought, the same thing more or less, that perhaps it is not Russian. Moreover, I didn't know it was a woman, but later someone told me, no, he's a man. He's not at all. Someone explained me, no, I met him and he's a man. But from where? Anyway, perhaps it is Russian, because I'm Cuban, I'm living in Mexico. My nationality now is from Mexico. Okay, no more discussion. This is the Lipschitz constant, but for alpha equal 1. But when alpha is inferior to 1, strictly inferior, everybody say Hölder. Today is the same thing. I don't have no time to explain, but using metric, general metric, it seems that it's the same thing Hölder than Lipschitz. But it's a condition that is very used in different problems in mathematics, in differential equations, in fact, Lipschitz spaces are very important for many different reasons, for applications in general, no? And then subsiste la 57. Ajá, el lema. Ajá, lema. Well, no, este no es el lema, es el 2. Esta de aquí. Ok, gracias, ahí mismo. Now, please, pay attention here. It is not exactly the same thing, but he Kalandiya said, if there exists a universal constant A1, it is not written sufficient but this is no problem. This is general constant A1 that satisfies this approximation. For each n, there exists a polynomial Pn that satisfies this inequality. If this is true, then Kalandiya, F is in the space Lipschitz alpha. It means the space of a function in minus 1 that satisfies the Lipschitz condition, or alpha, or Hölder condition. Then he proves that this Q that appears here satisfies this equation, where beta is any number such that 2 times beta is inferior to alpha. This is on one side, it is very important because it's the first result in that direction. But it has a problem that I will explain later. I will explain why. Did up to now. Later it will be more clear. When we try to solve inverse problems, we will see that there are. This is just what I was doing here, but I have no time to do that. When you have again here this space ellipsis alpha, this is bigger than beta. When we have this beta here, there is this, the difference is completely is ending the same also elliptic condition. We cannot approach all elements in alpha by beta element. Once you fix beta and alpha, there are functions in ellipsis alpha that cannot be approached from ellipsis beta, and this is the problem. In that time, neither Kalandiya nor anyone know about that. This was 2 or 3 years after that this was shown. And now many persons, mathematicians, tried to obtain inverse series by this way. Before to try to get inverse result, they were trying to obtain direct result. It means to approximate the functions f by polynomials in function of the parameter beta. This was still today, there are people working in that direction. But then you cannot obtain inverse result because of this reason. I will explain now. Okay, the first, okay, immediately, I'm not able never to follow a plan. I always take a look to the face pictures. If I understand, I continue. If not, I repeat. And it's the following. You know, the famous Weierstrass triangle. Yo creo, no. The following is function. There is a function in C2 pi here. Huh? There is a function in C2 pi that is not differentiable at any point. No? A famous example of Weierstrass. A famous example of Weierstrass. Bustamante, Cuban friend who worked with me in Puebla, and myself in an old paper, we proved what he wrote here, that this situation is true, and for this reason it is not a good idea to try to prove inverse theorems by this element of beta. But now we prove just a little more. This was a paper, not a paper, because I have no time to write it now, but we proved and presented this 4 or 5 months ago in a Havana conference, the following, that we will take here, I will repeat here better. Here you can find the two of them. Ellipsis alpha, here is ellipsis alpha, it's bigger. Ellipsis alpha is bigger, and there are functions here, ellipsis beta, such that you can find here functions that are nowhere dense in ellipsis in beta. It means that there not exist any point beta such that this function in alpha, in ellipsis alpha, satisfies the elliptic condition for beta. Yeah? It's incredible. It's the same thing because that Weierstrass here, but Weierstrass very far here, continuous function and differential. We prove that between more closed functions. Never mind how approaches beta from alpha. But the difference between that could be very, very small. But anyway, you can always find this function. This is a result that the proof is based in a category theory, using the category technique, ¿no? Como le dicen aquí a la categoría, using the bear theory, category 1, category 2. This is, I always forget what is 1 and 2, but I understand what is happening. I hope you are understanding also. Okay, no problem. Si se acaba la luz, yo sigo sin... Excuse me, Manuel, para la tarde búscate un borrador. Sí, aquí, lo podemos hacer sin esto, no pasa nada. ¿Ya? Ajá. Está muy bien así, así. Well, no problem. I will continue with myself. Better with the projector, but yeah, it's the same thing. Okay. Here you have.
Now it's working.
Yes. But how long? I don't know. So better here in this way, I believe. You can take here sub-norm or the knob of LP as you want. And we divide here, you know, the state of continuity. But we take T such that module T is in this way. No? And now this is, we call that, we write it, city alpha. Alpha is the parameter. I will take, I only will examine this case because when alpha is bigger than 1, there are many complications necessary to use high order difference here, and we can do it, but it's not important now for the idea. This F and delta. This is the soup. We take this as a modulus of continuity. This was an idea we had. I don't know, perhaps. I cannot claim that this was our idea, but in more than 10, 15 years, we don't know. We don't know any result, any such kind of modulus of continuity. Then, what is happening, which is that the function is in Hölder, the Hölder class, when this equal sup and delta, the alpha f delta is finite, no? Well, this is the Lipschitz condition that Kalandiya wrote, n of f. No? Well, we use it as the model of a continuity. And then Bustamante and myself proved 15 years ago or more, I don't know, that the best approximation, that we can prove that using here, for instance, the phi n that you wrote there from f to space Bn, which you use here the Cesaro means, no? Or the convolution with the Feyer kernel. There are many problems. I can write, it's no problem. This is the convolution to recover the function f. Using that kind of operator, we can prove the following: that ln f in ln in n is a model of a continuity, is B of B direct. And, or better, no, it's okay, that's the way. This is the direct result we found. And we were able to prove also that if a function satisfies that conditions, then it belongs to the Lipschitz class. Mm-hmm. But here is it. This is an old result, and we can prove it also for higher order parameter. This kind of result cannot be proved if we approximate the function with the parameter beta. Now, that's all. I would like to say that now there are many papers that still use approximation at the style of Kalandiya. But I don't know, Natig, I don't know what can we do with the wind theory and this new result. You see, Kalandiya solved the problem of the wind equation using this method. The method of approximation with the parameter alpha, the beta. I don't know, I'm not a physician, I don't know if we can improve the method of Kalandiya for solving the equation. I don't know. Certainly, he used his result, the lemma that we saw a few minutes ago, and with that he was able to find the solution. It is not exact, but it worked in his approximation, his method. I don't know. I don't know if we can improve that, because I don't know this equation well. Now, how many other results are in this direction? For instance, we can change. Well, the uniform approximation, Bustamante and myself wrote the paper for LP spaces also. And I have result directly with general group theory, topological group theory, and application to BS of spaces. No? That very useful in wavelet theory. There are many results in that direction. But my intention in this talk was the following, because it is a lecture for application or connected with physics problems. And since I work a long time in problem of Lipschitz spaces, to show you that the first result in that direction was done using a physics result, trying to solve the equation of the wing equation. And still now, today, there are papers that use this initial result from Kalandiya. Although it is not possible to obtain inverse theory in all cases, just because I showed you, I presented the results. It is not possible to approximate that. There is another important result. No time. No. It is there. No time. No. The following the problem. In this space that I presented you, in this equation I gave you, what mean Lipschitz? Okay, we know already. We know the meaning of this symbol, this space. But there, what is when I wrote there? I wrote also a small Lipschitz in the front here. What is the meaning of that? Just take a function f in Lipschitz this is alpha. If this tends to 0, when delta tends to 0, then we say f belongs to a small ellipsis. Huh? Why we introduce? We are obliged to do that because, and why nobody was able to obtain result that time? I explain immediately because reason. All the polynomial Pn, or trigonometric polynomial, or algebraic, the closure is the closure in ellipsis alpha is included different in general to ellipsis alpha. It means the polynomial are not dense ellipsis alpha. This is the reason for which nobody was able to obtain that result, and for which he were asking for all the kind of approximation. However, this is just a small ellipsis alpha. This is connected with other result for Shilov, the well-known mathematician. This is Russian, I believe. No, this is Russian real. No, Shilov and another. Moreover, the old theory that was done by for vectorial integral, vectorial measure, Bochner and all, was born studying this kind of idea, because the functions in ellipsis alpha are just exactly the one for which what is it? Okay. This function right here sub. We can write also in an integral, no problem. In general, that's not true. It tends to 0 only when the function f is in the small ellipses. Then the continuous translation occurs just in the small ellipses. This is the reason. And after this was proved only 3 years after Kalandiya, after the work of Kalandiya. And then after that were 2 ways. Anyway, I intended to express that the main role played by Kalandiya with his physical problem in the development of approximation by elliptic spaces. It was a crucial role played for that. And I invite physicians to be here to examine the Kalandiya method and to see taking a look with this new result, they can improve the method for approximation of the equation that it seems to me to be very important in Greek theory. Yes? It was only to show you this, to speak about this history. No more. If anyone is really interested, I can give 15 or 20 papers about without any problem. I can send by email immediately. Immediately, no, but just today or tomorrow. Okay? I believe if it's not, I'm very tired.
Some questions or remarks?
Ya se me perdió otra vez.
No question or remarks?
Okay.
Okay.
Thank you very much to everybody here.
So we have almost 10 minutes.